get started. As you see on the slide there, I created 4 columns in your Canvas grade book, A, B, C, and D. You'll see a number in those columns. If the number is less than 0, that means that's the grade you've earned so far in the course. If the number is greater than 0, that's the number of points that you need to earn to get to that grade. So far, remaining, we have 3 attendance quizzes, so that's 18 points. Exam 5 is 60 points, and then the final exam is 210. So there's 288 points left to be earned in the course. So as you start studying for the final exam, which is required, by the way, that's a university policy. You can check in the student handbook. You have to sit for it. So the average score on that is 60 points. So you can sort of bank on 60. Depending on how you calculate the grade, if you need more than that, I suggest you start studying now. But the average raw score is 20 on 7. So each question worth 3 points, so that's 60 points. If you want the study guide, you can buy that from Diane in room at 430. I think it's 28 bucks. Again, regarding the final exam, you have to sit for that. If you don't take it, regardless of whatever points you earn, I'm going to put an I for your grade in SOAR. If you're not familiar with that, that means incomplete. That means you're going to have to come back next semester and take the final exam. So I do not control access to those exams. So you have to take it on the day and time that the university schedules it. If there's an issue, it's beyond my control. And so if you do miss it, I'll reach out to you with an email. You're going to have to come back in the spring and take the final exam. So that I will sit on your transcript until you remediate it. So just make sure that you're on board with these policies. Any questions about the grades? Yeah.
I think in zip grade, we have a quiz that's not showing us their grade right now. It's model 5 lecture.
I'll release that when I question my office.
Thank you.
So the points that you see in Canvas are cumulative up until now. I'll go back and revise that on December 5th or 6th after you take your 5th exam. And at that point, everything's closed in terms of there's attendance quizzes and exams other than the final. And so those numbers will update, assuming you've earned more points between now and then. So the number in those columns will shrink according to your performance. Yeah. The numbers are the sum of all the required and bonus points. So everything is in there as seen. So the last week after Thanksgiving, I'll send out an announcement in Canvas basically asking you to audit your points. If there's an issue in terms of addition or subtraction or whatever, you can reach out to me and I'll go back through. If I don't hear from you, I'm going to assume that everything's correct. Other than those type of emails, I will not respond to emails asking for letter grade increases. So my advice to you is don't even write that email because I'm not going to respond to it. If you do write it, I'm going to report it to the dean of students as an academic integrity violation for asking for a grade roll. So the syllabus is pretty clear on what you need to meet in terms of the point cutoffs. And again, they're listed in terms of the grades, A, B, C, and D, what you need to get to. Any questions? So we just have today Wednesday is off, and then 2 more lectures, so 3 lectures total. We'll finish up the alkene stuff today, and then next week we'll do alkynes. So a couple more addition reactions. The first 2 are going to start with dihydroxylation. So if we're dealing with an alkene, so obviously in an alkene, the sp2 hybridized carbons are bonded to each other. And if we're doing dihydroxylation, that means each carbon is getting an OH, so that's a 1,2 diol. These are also called glycols. If you go on to biochemistry, you'll learn about triols, which are the acid component of fatty acid esters. So the other word that's used is vicinal, and again, that means a 1-2 relationship of the functional groups. The first reagent that will carry this out is called osmium tetroxide, so OSO4. And there's a picture of it shown. It's a sort of a translucent yellowish green crystalline solid. And what's interesting about it is it sublimes. So it goes from solid to gas phase without proceeding through the liquid phase. So that presents some challenges in handling it safely. One of the issues is that when it sublimes, it tends to target the eye. So people that work with it quite a bit, it'll sublime in the eye and like form cataracts and whatnot. So it's something that needs to be safely handled. If you look at the structure as drawn in red, you can see that it has more than an octet. And that's because osmium is a transition metal, and it has access to d orbitals that allows that. But overall, OSO4, there's an excess of oxygen, so it's an oxidizing agent. And as you approach the final, you know, when you're thinking about categorizing reagents and reactivity, those are things you want to look for. So there's no H in there, so you would say it's not a reducing agent. So the conditions with our model alkene, we take osmium tetroxide. We're going to use pyridine as a base. And then that solvent mixture, which helps solubilize everything. It's going to do a syn addition of OH to each carbon of the alkene. And then I say step 2, but really this means workup. So there's an intermediate that's formed that needs to be reduced down, and that's what the sodium bisulfite is used for. And that gets you your diol. And you have the top and bottom faces. So the reagent will dihydroxylate from both faces to give you a pair of enantiomers. And again, depending on the starting alkene, as you can see, we end up with both a tertiary and a secondary alcohol. Another reagent that will do this is potassium permanganate, which you may have seen in Gen Chem. It's a dark solid. When it's dissolved in liquid, it turns like a really dark purple color. And if you're not careful, it will stain everything it touches. The important thing to note about this, it's run under cold temperature. So you really have to control the temperature, keep it, around 0 degrees. As we'll see in a little bit, if it gets too warm, it will also react with the product to do something else. And that's sort of the second set of reactions we'll learn today. But again, it's going to do pretty much the same thing as the osmium tetroxide, probably a little bit easier to handle, less expensive reagent to use. So why is this important? So the 2001 Nobel Prize in Chemistry was awarded partially to Barry Sharpless at the Scripps Research Institute in La Jolla, California, for his work on chirally catalyzed oxidation reactions. And so you can see Professor Sharpless there on the left-hand side of the slide. And so, as we saw in the prior two reactions, the conditions will give you a racemic mixture. So you get dihydroxylation from the top and the bottom. And what he figured out was adding in a catalyst that will control which face of the alkene gets dihydroxylated. And so from those reactions, it's really only going to select either the top or the bottom face based on the catalyst. And so rather than producing a racemic mixture, you're getting one enantiomer. And so asymmetric catalysis, as defined by IUPAC, is a chemical reaction in which one or more new elements of chirality are formed in a substrate molecule, and which produces the stereoisomeric, either enantiomeric or diastereomeric products in unequal amounts. So really what a lot of research scientists do in these days are take the reactions that you learn in this class and render them asymmetric. So that just involves the normal conditions, but then putting a catalyst in there that's going to do some sort of selection. And so if you remember, we talked about EE, which was enantiomeric excess. Typically, you want that greater than 99 to 1. And just as a test case, so that would mean, say, 98R to 2 S. And I don't have it on the slide here, but the reason that's important is a lot of pharmaceutical prescription drugs, if they do have stereogenic centers, you want them to be the pure R or the pure S so that you're not throwing away like half the material. And just as an example of what we've learned, this is taken from one of Sharpless's papers. You can see at the top left here, those were the different types of alkenes we talked about. And then in the table, what is shown are cis alkenes. And so Sharpless basically took the osmium tetroxide, then you have the reducing agent in there with this alkaloid. So that alkaloid is the catalyst that will control either the top or the bottom face from which the osmium will attack. And so as you can see in the right-hand products, you get attack from the top face or the bottom face selectively based on these enantiomers of the catalyst you're starting with. So the alkaloid catalyst, as you can see from the model, how the alkene will sit sort of in the catalyst pocket by these sort of groups there. So whatever alkene you're starting with, you sort of put it into that model and you can predict which face is going to get dihydroxylated. Any questions? Yep.
How do you determine which enantiomer of that solvent is supposed to affect the face?
So that's a very good question, and that gets to like really what the challenge is. So how do you determine that this enantiomer is adding to the top face? To answer that, like practically speaking, that's probably where 95% of the research goes into in terms of time. So basically, once you have that, now you have to prove that absolute stereochemistry, that those OH groups are up. The easiest way to do that would be through X-ray crystallography. So that's basically like a snapshot of how the molecule looks in the absolute configuration. So the NMRs of these will look the same. So you can't tell by NMR if that center is R or S. They can do other things. You could potentially degrade this to something that's of a known absolute stereochemistry. But again, all of that takes time. So that's where a lot of the effort goes into. So I said with potassium permanganate, so KMNO4, you have to keep the temperature cold to get the dihydroxylation product. If it warms up, so when the temperature changes, what will happen now is that diol will cleave. So that's what you get when you keep the temperature cold. But if you warm it up, what will happen is now the sigma bond will cleave. And so this is called oxidative cleavage. And depending on the nature of what is bonded to those carbons, you'll either get a ketone, as seen on the left, or a carboxylic acid. So you can tell what you're going to get by looking at the starting alkene. So this one has 2 carbons. So that has to go to a ketone. The right one has a carbon and a hydrogen. So that has to go to an acid. So basically, whenever there's an H bonded to that sp2 hybridized carbon, it's going to go up in oxidation state. And so oxidative cleavage is important. And we'll see on the next couple slides another reagent that will do that called ozone. A couple questions on this first. I think we answered this. So ketone and acid. So of the ketone, what proton NMR data would you expect for that? So overall, there's 4 unique carbons. Since one of them does not have hydrogens, that means there's 3 unique sets of proton. And then we end up with a 3 to 3 to 2 ratio. So of this set here with 3 hydrogens, there's no neighbors, so that should be a singlet. Of that 3, there's 2 neighbors, so that should be a triplet. And of those 2, there's 3 neighbors, so that'll be a quartet. So we need, I think A is the correct answer. So your final exam will probably have 1 or 2 NMR questions on it. That's the kind of logic you want to use to answer those. So of the carboxylic acid, where would you expect to see the C13 signal of the carbonyl carbon? Since that's sp2 hybridized and it's in a carbonyl, that range will be 160 to 180. So this is a little bit of review. You'll recall when we talked about AZT and we were looking at oxidation states. We defined that as, looking at a carbon and then counting the bonds to a heteroatom. So a ketone has 2 bonds to oxygen, an acid has 3. So the sum of that would be 5. Any questions so far? So oxidative cleavage of alkenes. You're basically slicing the pi bond down the middle, and then each carbon of the alkene becomes a carbonyl. Probably the most common way to do that synthetically is with ozone gas. So ozone has that structure. So 3 oxygens, and then 2 of them have the formal charges. The solvent that we use is typically dichloromethane, and then we use a cryogenic bath of -78. So that comes from a mixture of acetone plus dry ice. So that will make a slush that gets you down to -78. And so you take your alkene, dissolve it in dichloromethane and chill it, and then you bubble in ozone gas. And eventually it'll reach a blue color. And then that's when you know that you're done adding the gas. And at that point, you have to do a workup. And so the workup consists of a reducing agent, so dimethyl sulfide, or triphenylphosphine. So notice the difference now in the workup conditions. Ozonolysis under the reductive workup will either give you a ketone or an aldehyde. So even though that carbon there has an H, it's not getting oxidized up to an acid. It's staying at an oxidation state of 2. And that's due to the reductive workup conditions. If the workup conditions were different, say we added hydrogen peroxide instead, then that aldehyde would be oxidized to an acid. So you have to pay attention to all of the reagents that are listed. So to give you an idea of how this happens, because ozone has 3 oxygens, your products each end up with 1 oxygen. Where does that the third oxygen go? So ozone is known as a 1,3 dipole. So there's 3 atoms, and it's dipole due to those formal charges. So we have this negative charge that will attack a carbon. Then the pi bond will act as a nucleophile to attack the terminal oxygen. And then we break that pi bond between the 2 oxygens. And that's what's known as a 3+2 reaction. We're just counting the atoms there, so 3 from ozone, 2 from the alkene. So that's going to form a 5-membered ring. And so you can see we're not quite there yet. Each carbon atom has an oxygen, but there's still the 3rd oxygen. We need to get rid of it, and we need to form the carbonyl groups. And so that has a name called a mole ozonide. And so that's formed, but then it will degrade after it's formed to form another intermediate. So if we push electrons down, we're going to form an OC pi bond. We're now going to break the carbon-carbon sigma bond and break an OO sigma bond. So we form those 2 things, but again, we're still not to the end. And essentially what will happen, this looks like it could be a final product, but it's not quite there yet. Maybe what I'll do is I'm just going to flip this so that we can draw the next intermediate that happens. So I've just flipped around that aldehyde. They'll recombine. This negative will attack that carbon of the carbonyl. This pi bond will attack that, and then we'll break the CO pi bond. So they recombine to form another 5-membered ring. And so now that's called an ozonide. So now we're in a little bit better shape to get rid of one of the oxygens. And so we do that with a reducing agent. So if we're using the dimethyl sulfide, the easiest bond to break would be the oxygen-oxygen sigma bond. So we have the sulfur attack that. We break the OO sigma bond. We reform a carbonyl pi bond. We form the second pi bond, and then oxygen's actually going to end up with an extra lone pair. So overall, the sulfur atom itself is getting oxidized. That's where the third oxygen ends up. So our oxidation states are 2 and 2. We end up with a ketone and an aldehyde. So overall, I mean, that's the mechanism, but what you should be able to do is just look at your starting alkene and predict, are you going to form ketone or aldehyde? What will the products be based on the groups bonded to the alkene carbons?
Do you mind re-explaining how you count the oxidation states? Like on one side, I think you have 3.
So for the ketone, if we're looking at that carbon, because it's bonded to oxygen, so we're counting 1 bond, 2 bonds, so that gets us the 2. So a carboxylic acid, so now we have 3, so that's going to be 3. So carbon dioxide is 4. So if you go on to take 256 next semester with me, the modules are broken up according to oxidation state. So we'll go through, look at OS1, OS2, OS3, and then we learn the reactions for those oxidation states.
So if there's another double bonded oxygen, like a completely separate part of the molecule, would that still add to that number? Like, even if it's not near that area?
Yeah, for overall the molecule, yeah, you would add just to get an idea of the overall oxidation state, but you sort of do them individually. So in terms of those two products, what IR signal is indicative that an aldehyde was indeed produced? So they both have carbonyls, so that's your 18 to 1700 stretch, but the aldehyde has a special one. That was this H, so CsP2H. That occurred to the right-hand side of your normal sp3H stretching. So you'll have that sharp signal around 2750. So here's an example straight out of your book. We have a diene, so that's 2 alkenes, subjected to ozonolysis with reductive conditions. And it says what functional groups would be produced. So let's look at each alkene, see what's bonded to it, and that will help us predict. So the alkene highlighted in red this carbon has 2 carbon substituents. So when you slice through it, that's going to end up as a ketone. The other one's 2 hydrogens, so that's going to end up as an aldehyde. On the other side, that carbon has 2 carbons, so that's a ketone. That has a carbon in an H, so that's an aldehyde. So we would get B, 2 aldehydes, 2 ketones. And if we drew that out, those would be the products. So keep in mind, if you're starting with a cyclic alkene, the ring is tethering those 2 functional groups together. So right here, when you clip there, that functional group is still tethered to that one through the ring. Any questions before we move on? So the last set of reaction conditions are going to use a new reactive intermediate called a carbene. So thus far in the semester we've seen carbocations, So those are electron deficient. We've seen radicals. Those are neutral. So single electron. Carbanions. That's when carbon has a lone pair, it's negative charged. And then the new one is called a carbene. So these are also neutral. But now the carbon has what looks like a lone pair. So here's the structure of the carbene. The reason it's not negative because there's only two substituents bonded to that carbon. If it had a third one, then it would have the negative charge on it. So one carbon bearing two substituents and a lone pair is called a carbene. So they're divalent and neutral. So always remember that when we're talking about reactive intermediates, on the energy coordinate, they exist in the well. So the transition state was the highest part of the hill, the trough or the valley before the product, that's the intermediate. So that because the carbon atom is reactive and it's one atom now, it's going to essentially react similar to epoxidation where each carbon gets a bond to that oxygen. Now each carbon atom of the alkene gets a bond to that carbon. So there's three atoms involved. These make cyclopropanes. So this is called cyclopropanation. And that's a three-membered ring. And these are of interest because they're strained. And it's a reactive functional group that you can do other things with afterwards. So of your starting alkene, the cyclopropanation happens in the syn, so from the same face, synchronous fashion. The bonds from the two carbons of the alkene bond to that carbene carbon from the same face at the same time. So there's three methods to do that. Diazomethane, Simmons-Smith, and haloforms. So notice that all of them have one carbon atom. And that's the carbon that's deposited in the reaction. So diazomethane is typically prepared immediately before it's used. It's a fairly toxic gas. It's run in diethyl ether as the solvent. And essentially what happens, so here's the Lewis dot structure of it to the left here. So Lewis dot structure. Here's a resonance form. And if you add heat or light, it will basically decompose to lose nitrogen gas. If you look at that arrow, that's called alpha elimination. So there's enough energy from the heat or the light to cleave the CN bond, and now you form your carbene. And so notice it's just CH2. And so you can react that with the model alkene to get enantiomeric cyclopropanes. So as I said before, a lot of reactions are called named reactions. So Sim and Smith were two chemists that discovered these conditions where you can take diiodomethane. So there's diiodomethane, zinc and copper chloride. That will form, I guess, an amalgam that reacts with the diiodomethane to decompose that to give you your carbene. And one of the benefits, again, to using this, as I said, diazomethane, it takes some skill to generate it. And again, you can't do it on large scale. It has to be very dilute conditions, and that can be challenging to carry out. So these conditions are a little bit easier to do in the lab. Again, it's a syn-synchronous addition, and you would get enantiomeric cyclopropanes. There are ligands that exist, as we saw with the sharpless chemistry, that will allow you to select one face over the other when you do this. But then again, the hard question is, how do you know which one you got in terms of figuring things out? And as I write here on the bottom, this is also a stereospecific reaction. See the relationship of the methyl to the ethyl? That's what you're starting with in the alkene. So because this happens syn-synchronous, that's retained in the product. And the last way to do this, another common way, is to use a haloform. So a haloform is just a general form of a trihalomethane. So you've probably heard of chloroform. So CHCl3. Because that carbon has 3 halogens bonded to it, the H is pretty acidic. So when you treat it with a base, that base will abstract that proton as shown here. So acid-base reaction. Now you end up with this carbanion that will do an alpha elimination. So basically, we're going to cleave that bond. So X minus leaves. And now the difference with this carbene is that those atoms are both halogens now. So the same mechanistic considerations. You end up with the cyclopropane, but now it's geminally substituted. So remember, vicinal means 1, 2. Geminal means 1, 1. So you have a 1, 1 dihalocarbon. Any questions? So the last 10 minutes, what I thought we would do is just sort of put all this together now that we've seen some reactions, put together some sequences, see if we can take the starting materials to the products. So if we wanted to take cyclopentane and make cyclopentane oxide, what sequence of reactions could we do that with? probably what's most difficult in starting off in learning this. There's the start, there's the end. Notice there's only CC and CH bonds here. But you're ending up with carbons that are oxidized. So you have an oxidation state of 1 and 1, but you're starting with 0 and 0. So rather than try to think in a forward direction, we'll think from the product and then move backwards. And so a lot of this will rely on, the words of the functional groups and then the reactions. How do you make them? So we know this is an epoxide. And so that arrow means retrosynthesis. So we know that an epoxide can come from an alkene. So to go from the alkene to the epoxide, we would use MCPBA. So that would eliminate C and D. How do we make alkenes? We can make those through beta elimination of an alkyl halide. And then how do we take an alkyl halide to an alkane? That was radical CH substitution. So overall, between A and B, B would be the most appropriate because we learned fluorine was not good for CH substitution. So really the way to start connecting all of these dots, I think, is to do this approach of thinking backwards to the starting material and identifying the functional groups along the way and what reactions make those functional groups. Any questions on that one? So I just ripped these next ones straight from your book. We want to take a secondary bromide and make a primary alcohol. And I think I screwed up this structure here. Yes, I did. So it should be that. So what can be tough about this, so that carbon's at oxidation state 1. That one's at 0. Now in the product, this is oxidation state 1 and that's at 0. So we've changed what carbon's oxidized, what's reduced, and then the nature of the functional groups. But if we think backwards, we have a primary alcohol. So we know that to get a lesser substituted alcohol, we can use hydroboration oxidation. So between those two carbons, we would stick an alkene. So that would be hydroboration oxidation. We know that we can make an alkene from an alkyl halide using the beta elimination. Now, but the issue here now is which base do we choose, because we want the lesser substituted alkene. So this would be a Hoffman elimination. So we'd have to use the bulkier base. So potassium tert butoxide. So in the forward direction, this would be step 1, this would be step 2. So I think we have time for one more. This is like the first one we did. Stick a halogen in there, eliminate it, epoxidize it. Bob's your uncle. So what about this one? So cyclopentane to now this dialdehyde. So right off the bat, you notice that you're going from something cyclic to acyclic. So you have to open the ring, and then 2 of the carbons are being oxidized. So there's 5 carbons total in the ring, there's 5 carbons total in the product. We could make that through ozonolysis. So if we take cyclopentene and then cleave it, that would give us the dialdehyde. And then we've seen already a couple times, how do we make the alkenes? That's the elimination. So an E2 mechanism. And then how do we get the bromine in there? So that would be Br2 with light or heat. And so that's the radical CH substitution. So really, for a lot of these, the take-home message is that if you're just starting with CC and CH bonds, you have to do this type of reaction first. A CH to CX, so you get a polar bond in there that you can then do something with, whether it's SN2, SN1, E1, or E2. And then once you have the alkene, that's where all the addition reactions come in. So a way to practice this, use these mind maps where you sort of start with something central. Then you build off, and you're just practicing, what do you remember about each of those functional groups? What reactions can they undergo? So we are out of time. You do have a quiz. There's some candy if you want. Please take some so I can get rid of it.